Hello everyone, I am Dr. Shawana Tabassum, an assistant professor of electrical engineering at the University of Texas at Tyler. And today I'm going to talk about our project on IoT-enabled electronic textile-based flexible body sensor network for real-time health monitoring in assisted living during pandemic. And the authors of this paper are my graduate student, Nafize Ishtiaque Hossain. He's a master's student in electrical engineering, and myself. So here's the outline of this presentation. First of all, I'm going to talk about the motivation of this research. Then I'm going to present the system configuration, the configuration of the overall system. Then I will explain the fabrication of the device that we have developed. And then some characterization results, some practical application with the device and the system that we have developed, and finally, some future prospects of our research and conclusion. Okay, so now I'm going to talk about the motivation of this research. And first of all, I'm going to explain the current research gap. The global wearable technology market is proliferating rapidly with an anticipated value of USD $70 billion by 2025. So as we can see, it's a huge market. The connected miniaturized wearable devices, they are expected to revolutionize the future disease management and clinical decision making. That's why it's extremely important that we design these wearable devices which can track our health status in real time and can send that information to the clinician, right? However, these wearable devices, whether these are the commercial ones such as Fitbit, Apple Watch, Google Glass, or the ones which are under research, they suffer from some limitations. For instance, these devices are mostly limited to smartwatches and straps. Now, there has been some research which demonstrate that the elderly population, they are kind of reluctant to wear these external wearable devices because they cause irritation, itching, and also interrupt their physical activities and daily routine. And that's why the elderly population are not willing to wear these external devices. Now, an attractive alternate could be electronic textile, because as you can imagine, if we can embed the sensors or devices into a cloth, then the elderly people can easily wear that cloth and at the same time have their fitness monitored in real time. Now, these electronic textile based devices, they also suffer from some limitations. For example, they require complex fabrication and clean room, which is often not feasible for low resource settings. So where is our contribution then? So our contribution is to develop a flexible body sensor network on textile using a very low cost and clean room free technology. Now, although progress has been made on two-dimensional film-like architecture which are woven into fabrics, but one-dimensional fibers are more attractive because they provide a high aspect ratio, they are highly flexible, they are lightweight, and they can be easily embedded into the textile in different shapes. So that's why in this work we have developed a one-dimensional fiber-based strain sensor, an array of them, and then we have integrated them into a textile using a very low-cost method. Ours is a very simple two-step procedure. And we have also incorporated wireless communication so that data from the sensors can be wirelessly transmitted and uploaded to the cloud for further analysis or access by the care provider. Also, we have demonstrated several applications with our strain sensor, such as monitoring body movement, monitoring speech, cuff patterns, and also monitoring subtle movements such as eye blinking. Okay, so here's the system configuration. So as I mentioned in my previous slide, we have developed an array of strain sensors and embedded them into a textile to develop a flexible body sensor network. So as this diagram or schematic shows, each individual will have an array of strain sensors embedded into their cloth, And then these array sensors will perform different tasks, like they will measure different body movements such as finger kinematics, then cuff pattern, speech pattern, or eye blinking, etc. And then all these informations will be sent to the cloud via LoRa. So each of these FBSN, they have a LoRa module on board, and then all these LoRa sensor nodes are communicating with the cloud through a LoRa gateway. And then all these information, all these body movements and real-time measurements can be accessed by a primary care provider in real time. So that's how the overall system works. So this slide shows the step-by-step device fabrication process. We used a very simple two-step fabrication process, as you will see here. We started with a bare nylon fiber, which was commercially available, and here this picture shows the optical microscopic image of the bare nylon fiber. And then we coated this bare nylon fiber with reduced graphene oxide. So we prepared different concentrations of reduced graphene oxide, and then we found the optimum dispersion that we used to coat the bare nylon fiber with. And finally, after we coated the nylon fiber with reduced graphene oxide, we sewn it into a textile. As you can see here in this third figure, the fibers were sewn into a black textile, and then this e-textile sensor was interfaced with the LoRa board, and finally the results were communicated to the cloud. And here on a smartphone blink application, we can see the real-time measurements. So here this graph shows real-time finger measurements, and the inside at the lower left corner, it shows how the finger was bent with the sensor mounted on the finger. So this picture clearly shows the complete setup of our system. We did further characterization of the sensor. So for example, we applied tensile and bending strain for 100 cycles. Figure A shows the durability test under 100 cycles of stretching, and figure B shows the durability test under 100 cycles of bending. So in both of the cases, we can clearly see that the resistance of the sensor didn't vary much even after 100 cycles of stretching and 100 cycles of bending. And here C and D, they show one complete stretching cycle and bending cycle respectively. And here also we can see the minute variation or negligible variation in the sensor response under stretching or bending motions. So we can clearly say that our sensor is highly reproducible, and this is also confirmed through the hysteresis cycles, hysteresis plots shown in E and F. So E shows the hysteresis at 100th stretching cycle, and we can see that even after 100 cycles of stretching, there is very small amount of hysteresis observed, and the hysteresis was even smaller for bending motions. So as we can see that even after 100th bending cycle, the hysteresis was very small. So from these tests, we can confirm that our sensor provides highly reproducible behavior even after 100 cycles of stretching and 100 cycles of bending. So after characterizing the sensor, the same RGO coated nylon fiber which was sewn on a textile was used for a variety of applications. So all these results are demonstrated here in this slide. Figure A, it shows the real-time finger bending with the sensor. The sensor was mounted on one of the fingers, and then the finger was bent at different degrees. And here we can see that the resistance variation of the sensor was proportional to the degree of bending. And this kind of real-time monitoring will be very useful for applications such as soft robotics. So for example, if we want to monitor and adjust the kinematics of soft robotic fingers, then we can simply mount this textile-based sensor in one of the fingers, and we can monitor the bending in real time. Then figure B, it shows the real-time monitoring of eye blinking, which is a very subtle muscle movement. So we can here clearly see that our sensor is capable of tracking or picking up the subtle muscle movements. So as we can see, when my eyes are open versus when my eyes are closed, during this eye reflex, my sensor was able to pick up that variation, as we can clearly observe here in this figure B through the resistance variations. And this kind of real-time monitoring will be very useful for driver drowsiness monitoring. When someone is like alcoholic and is driving the car and they are feeling drowsy, so when their eyes are reflexing, then if we can have a textile-based sensor mount on here on the face, there in the temple area of the forehead, then it will be very useful to pick up that eye reflex in real time. Then C shows how using the same sensor we were able to monitor the speech in real time. So for example, when the sensor was mounted on the throat and then the user was uttering the three words hello, graphene, oxide, then the sensor was capable of picking up those variations in real time. And we can also see how the sensor response and the pattern was different for these three different words. So it can clearly distinguish the words. And this will be very useful for human-machine interface. So here I'm talking more about the broader impacts of this sensor that we'll be working with in the future. And then the figure D, it shows real-time cough pattern monitoring with the same sensor. So again, the sensor was mounted on the throat and then the user was coughing at a certain frequency, and we can see how the sensor was capable of picking up that pattern of cough. So here it's very obvious that this kind of real-time monitoring of cough pattern will be useful for COVID-19 monitoring. So here we can clearly observe the broader impact of this and future prospects of this kind of sensors. And another thing I would like to mention here is, like, even after 200 cycles of bending and 200 cycles of stretching, the sensor response was pretty much stable and identical. So again, it clearly shows the excellent reproducible behavior of the sensor. So even though from the previous slide we can see that our sensor was capable of distinguishing different words, but we really wanted to quantify that. And for that we analyzed the real-time measurements and applied correlation algorithm in order to find the cross-correlation coefficient between uttering different words. And also at the same time we also wanted to see how well the sensor can differentiate between emotions. So these results are shown here in this slide. So from A to F, they are real-time measurements. So A is the dynamic sensor response for saying the word you with normal emotion. Then B shows the sensor response for saying the word your with again normal emotion, and C shows the sensor response for uttering the word us with normal emotion. So for this experiment we chose these three words, you, your, and us. And then D, E, and F, they show the sensor response again for the same three words but with different emotions, like sad emotion, happy emotion, angry emotion. So when the user is uttering the same word, let's say you, with different emotions, when he is sad, when he is happy versus when he is angry, then we wanted to see how well our sensor can respond to these different emotions and how well the sensor can differentiate between different words. So let's see in the next slide what cross-correlation coefficient did we find for each of these emotion versus separating different words from each other. So this slide shows the cross-correlation coefficients for different emotions. So as you can see that the cross-correlation between different emotions with the same word uttered was found to be pretty close to 1, which is expected, right? So here, for example, the first row, it shows when the user uttered the same word you with two different emotions, like sad versus normal, then the cross correlation coefficient was found to be 0.9916, pretty close to 1. And likewise for other emotions, like normal versus happy emotion, normal versus angry emotion. And similarly, when the user was saying the word your with different emotions, then we found their cross correlation. And likewise for the word us. And in all of the cases, the cross correlation was pretty close to 1, which means that our sensor can pick up the word that the user is uttering regardless of the emotion. And here a cross correlation value of a value which is closer to 1 means there's higher similarity. The closer the value to 1, the higher the similarity, and that's what we are seeing here. So again, to summarize, our sensor was capable of differentiating the word regardless of the emotion. That's what we can see in this slide. And then here this slide shows the same cross correlation study but between different words. So for example, here we uttered all the words in normal emotion. So here the emotion was fixed, but the words were different. So for example, the cross correlation value between you and your was found to be 0.8571, whereas the cross correlation between the two words your and us, which are very different, was found to be 0.4829. So as we can see from the cross correlation values, you and your were highly similar, and that's why the cross correlation value was close to 1, whereas your and us are very different, and that's why the cross correlation value was very much less than 1, only 0.4829, which means that you and your are highly similar and your and us are less similar, and this is clearly confirmed from our sensor results. So here, to summarize, our sensor was clearly capable of differentiating between words. And finally, we did some comparative study, like we compared the performance of our sensor with some existing very recent fiber-based sensors, thin film coating based sensors. So for example, Chang et al., they reported a graphene oxide based sensor, strain sensor, which did not have any wireless connectivity, and the gauge factor, which is the sensitivity of a strain sensor, was found to be only 3.7. Then the second row, which shows the work from Zheng et al., they reported PDMS, PU, titanium, gold based strain sensor. Also, it didn't have any wireless connectivity, and the gauge factor was again found to be very less, only 4.91. And in both of the cases, the fabrication process entailed complex procedure and clean room, the requirement of clean room, whereas in our case we used a very simple two-step procedure, as I mentioned in one of the previous slides, and we did not use any clean room for fabricating our RGO coated fiber. So we used reduced graphene oxide, and as I mentioned, ours is a very simple two-step procedure. We also incorporated wireless connectivity, and even then we were able to get a gauge factor of 6.24, which is higher than what is reported in the literature. So here, figure A, it shows the calibration plot of RSSI value versus the distance of the user from the LoRa gateway, and then B shows the estimated distance versus the actual distance. So here we can clearly see the RSSI value could accurately estimate the distance of FPSN nodes with a very high Pearson correlation coefficient of 0.996. So that's all about my presentation. If you have any question, please feel free to reach out to me here in my email at tabassum@utttyler.edu, and I'll be happy to take any questions you might have. Thank you very much for your time.